All right, this is Lab 4 on oscillation. Introduction. The purpose of this lab is to analyze the motion of a swinging spring mass system and verify that the energy principle and Newton's second law can accurately predict the trajectory by comparing our tracker and glow script model to real life. The fundamental physics principles used in this lab include Newton's second law to iteratively update the velocity and position of the mass, and the energy principle to track the conservation and transfer of kinetic, gravitational potential, and spring potential energy. My computational model uses Newton's second law to update the mass's velocity and position at each time step, and it applies the energy principle to track the kinetic and potential energy changes, ensuring that the total energy of the system remains conserved throughout the oscillation. The main physics ideas here. In this experiment, we use Newton's second law to predict motion. By calculating net force from gravity and the spring, the velocity update formula tells us how the speed changes, and the position update formula tells us the next coordinate. We also use the energy principle to ensure total energy is conserved. Because there are no significant external work-doing forces, we expect the total change in energy to remain zero throughout the motion. With that being said, we'll look at the initial conditions of our experiment. So in this case, our system is comprised of the mass, the spring, and Earth. That way we have no external forces like gravity acting on our spring mass. The initial position was recorded as negative 0.113 and negative 0.635 meters, with the mass starting from rest, so initial velocity was 000 meters per second. These coordinates and the velocity were exported to a CSV file to be read by our glow script code for the experiment, allowing us to model what theoretically should happen. The experiment. In this experiment, we observed a video of a spring with an attached mass oscillating around a fixed axis. We used tracker, a CSV file, and a glow script model to model this motion, using update formulas and the energy principle to ensure energy was conserved. The code was quite difficult compared to the others, but it paid off as the results were really cool to see. Over here on the right, we see the CSV file, and there were quite a few rows to fill in. All right, looking at the code. My computational model functions by using the velocity and position update formulas derived from Newton's second law to predict the mass's trajectory while simultaneously calculating the change in kinetic, gravitational potential, and spring potential energies to verify that the total energies of the system remain constant. This code was quite a bit harder to fill in than previous labs, but to see it pay off was well worth it, as it returned a few graphics that were very cool to see. The graphs up here were a lot cooler than some of the past ones, so I like this one. Predictions versus reality. I observed that my experimental results relatively closely matched the predicted oscillation periods in both the x and y directions, confirming that my initial setup and calculations for the spring constant and relaxed length were accurate in representing the physical motion. My results weren't exactly the same, but they were close enough for me to conclude that the experiment was a success. Sources of potential error, of course, include human inaccuracy in clicking the center of mass and tracker, the fact that we simplified the mass of the object to just be a point mass, and other things that we didn't include, like air resistance. In a nutshell, in doing this lab, I had to see if I could code a simulation that matched a real video of a mass swinging and bouncing on a spring at the same time. Plugging in Newton's second law to handle the movement and the energy principle to track how energy swapped between kinetic and potential, I was able to prove that the computer's prediction lined up very closely with the actual data. I'm going to kind of blast through some of these because I'm running out of time. All right, for my what does it mean questions. For the first one, yes, the energy principle is satisfied because the change in total energy represented by the orange line in my glow script graph remains constant at 0 throughout the entire simulation. On to the next one. To estimate the periods, I looked at the position time graphs from tracker and averaged the time over 3 full oscillations to get an average period of 1.64 seconds. To estimate the periods, I looked at the position time graph from tracker and averaged the time over 3 full oscillations to get an average of 1.64 seconds. Overall, we see that there are some different forces acting on either of the two, so we're going to get slightly different types of movement. Therefore, we're going to get this non-circular oscillation here. My main takeaway is that as long as I set up Newton's second law and the energy principle correctly in the code, I can actually predict a pretty messy looking 2D motion with a high degree of accuracy. It was cool to see that even though the mass was swinging like a pendulum and bouncing like a spring at the same time, the total energy stayed at 0. The total energy change stayed at 0, proving that the model and the real world physics were totally in sync.